Welcome back to the deep dive. You've sent us the white papers, the research, and the internal source material, and we are ready to turn that complex knowledge into surprising, actionable insights.
And today we're doing a really fundamental architectural deep dive. We're looking at the next evolution of sequence models through this new general framework called Miras.
That's right. And our mission really is to unpack how this framework gives you a complete toolkit for building these models. A toolkit designed to get around the two biggest problems in the field today.
Right, you've got the computational explosion of transformers on one side.
And the memory limits of the recurrent models on the other.
Exactly.
So that's the real problem, isn't it? Transformers, they're the state-of-the-art, the workhorses, but everyone knows their Achilles heel is long sequences, that quadratic time and space complexity.
It's a killer. I mean, the cost doesn't just grow with the context length.
It explodes.
It explodes.
Yeah.
If you double the length of your input, you quadruple the compute cost.
Yeah.
And that just fundamentally limits you. You can't easily model, a full book or a massive code base.
Which is why we've seen this recent wave of linear RNNs, right? The idea being they are super efficient because they compress everything down into a single fixed-size memory vector.
A great idea in theory. You process one token at a time, you update your state, you get that nice linear scaling.
But there's always a but.
Always a but. If you have to cram let's say a 30,000-word document into one fixed-size vector, you hit what we call the bottleneck of compression.
Information just gets lost or scrambled.
Precisely. And this is where the Miras framework comes in with a pretty fundamental rethink. And it's drawing its inspiration from, well, the human brain.
Always a good place to start. So what's the core analogy here?
The framework basically says, look at all these successful models, LSTMs, Mamba, Titans, all of them. It reconceptualizes them as being essentially associative memory modules.
So their main job isn't calculating, it's learning to map inputs to outputs, keys to values, and storing that knowledge.
Exactly. And the core design principle it pulls from cognition is something called attentional bias.
Right, the natural human tendency to prioritize. You're in a noisy room, you hear your name, and everything else fades away.
That's it. And Mira says the model has to be built to do the same thing, to prioritize certain tokens or events. The way it does that, the way you encode that bias mathematically, is through the model's internal objective function.
The loss function.
The loss function, the math you choose to measure error. Well, that inherently decides what the memory focuses on and how it learns.
Okay, let's unpack this. The name itself, Miras, translates to legacy in a few languages: Persian, Arabic, Turkish. And it's meant to be just that, a lasting blueprint. And it boils everything down to 4 critical design choices.
Think of it like a builder's palette. Anytime you design a new model in this framework, you have to consciously pick these 4 things.
Okay, first up, memory architecture. So what actually holds the information?
This is all about capacity. I mean, what's the structure? Is it a simple vector, a flat matrix, or are you going for something much more expressive, like a multi-layer perceptron, an MLP, for your memory? The more complex the structure, the more nuanced the learning can be.
And that choice leads right into the second, and maybe the most important one, the attentional bias.
This is where you mathematically define your priorities. It's the memory's internal loss function. Are you just trying to minimize the average error with, say, an Eltane-2 regression loss, or are you trying to be robust to outliers where something like Huber loss would be better?
I see. So if I pick a standard Heltel loss, my model is basically trying to be a good student on average, treating all mistakes equally.
Precisely. But if you choose something else, you fundamentally change what the model cares about. Which brings us to number 3, which is absolutely critical for long-term memory: the retention gate.
Okay, this sounds like how we deal with that fixed-size memory problem.
It is. It's the mechanism that decides whether to keep the past state of the memory. But it's not just a switch. It acts as a regularizer during the update. It's what stops the model from learning something new by completely overriding something important it learned before.
So we're talking about things like elastic net regularization, KL divergence, powerful stuff.
Right. And then finally, number 4 is the memory algorithm.
This one sounds a bit more straightforward.
It is. It's just the optimizer you use to learn the mapping. Gradient descent, GD with momentum, maybe even something more advanced like Newton's method.
What's so amazing is when you apply this lens to the current models out there, the source material has this table 1, and it shows that almost all of them, RetNet, Mamba, DeltaNet, they're all using basically the same kind of attentional bias.
It's either dot product similarity or an L2-2 regression objective. They're all fishing in the same pond, using the same mathematical tools for prioritization. And Miras just blows the doors open and says, what if we optimize for something else entirely, like robustness?
Which brings us perfectly to the second big idea here, which is all about that retention gate. What's fascinating is the conceptual shift. It's about how we think about memory management.
It's a huge shift. For years, in LSTMs and so on, we've talked about the forget gate.
Right.
Miras reframes that completely. It's not a forget gate, it's a retention regularization. The model isn't deciding what to forget. It's actively deciding what not to let go of. It's a decision to maintain knowledge.
That feels so much closer to the human analogy, right? When we can't recall something, the memory isn't necessarily gone, it's just inaccessible, a retrieval failure.
Exactly. The framework suggests that's what's happening in the network. The problem isn't just capacity, it's retrieval and management.
And that's why you can justify using these more complex retention mechanisms. Like, let's talk about KL divergence.
Okay, so KL divergence, at its heart, measures how different one probability distribution is from another. Using it as a retention gate forces the memory variables to stay within a scaled probability simplex.
Let's unpack that. Why do that? What does that get you?
It's really a clever trick to prevent numerical instability. When you're recursively updating memory over thousands of steps, things can explode or vanish. By using operations like softmax, you force the memory weights to behave like a probability distribution. They have to sum to a certain value. It keeps everything balanced and stable.
So it's a way to enforce discipline on the memory. What about the other choice? Elastic net regularization. That one sounds like it offers the best of both worlds.
It kind of does. It gives you soft forgetting, which is like gradually turning down the volume on old memories by scaling them. But it also gives you hard forgetting.
Hard forgetting.
Yeah, it uses a mathematical tool called a soft thresholding operator. And what that does is it takes any small, insignificant values in your memory and just sets them to zero. Gone.
So you're not just dimming the lights, you're actively cutting the power to things the model decides are irrelevant.
Exactly. True erasure of low-priority data. And this connects back to the first pillar, memory architecture. The really high-performing models, like Titans and these new Miras variants, they don't use simple vectors or matrices for memory. They use expressive MLP architectures.
But doesn't using a whole MLP for your memory slow things down?
It's a trade-off. A simple memory is fast, but it can't capture really complex relationships. An MLP memory is much more expressive. It's almost like a little meta learner inside the model, updated with gradient descent. It's just far, far better at storing and retrieving nuanced information.
Okay, here's where it gets really interesting. The 3 new models they built to show what Miras can do, models that go beyond that standard L-to-2 regression.
Right, Moneta, Yaad, and Memora. And all 3 of them use that powerful 2-layer MLP for their memory. They're showcases for the other 3 pillars.
Let's start with Yaad. The source material frames this one as being built for robustness. We're dealing with outliers or extreme events. What makes it so tough?
Yaad uses Huber loss for its attentional bias. You can think of Huber loss as a cognitive coping mechanism. If the error for a given token is small, it acts just like a normal altitude loss. It cares about precision.
Okay.
But if the error is huge, say it hits a really noisy token or something totally unexpected, the loss function smoothly shifts its logic over to a normalized L$1 norm.
And what does that do in practice?
It massively reduces the penalty for that one big error. An $1 loss would penalize it quadratically, which makes the model freak out and distort its entire memory just to fix that one outlier. The L$1 logic is linear, so it learns from the outlier without letting it wreck the whole memory state. It makes it robust.
That's a perfect example of tailored design. Okay, what about Moneta?
Moneta is all about generalization. It uses the generalized L-Toller attentional bias. So in their experiments, they used P33 for the attentional bias and Q404 for the retention gate.
So why should you, the listener, care about those specific numbers?
Well, the numbers themselves aren't the point. The really key insight from their studies was that they found no simple monotone pattern when they changed P.
Right.
There was no single best value.
Which proves the whole philosophy of the framework.
Exactly. It validates that there's no single best similarity metric. The right choice depends completely on the task you're trying to solve. You have to tune it, which is something standard models just don't let you do.
And the third one, Memora.
Memora is the showcase for the retention gate. It uses a simple standard 72 regression loss for its attentional bias, but it pairs that with the really sophisticated KL divergence for retention. And like we talked about, that brings in the softmax operation and keeps the memory stable and balanced over long sequences.
Okay, before we get to performance, the elephant in the room. These models are recurrent, they're nonlinear. That sounds painfully slow to train compared to a transformer. How did they get around that?
Ah, yeah, that's a crucial piece of the puzzle. They use a very clever parallelization trick. They chop the sequence up into small chunks, say 16 or 64 tokens. Then they process a whole chunk at once. The trick is that the gradient for all the tokens in the current chunk is calculated based on the final memory state from the previous chunk.
So within that little window, the memory state is treated as fixed.
Exactly. It's a local linearization. It lets them bypass the sequential bottleneck just enough to parallelize everything efficiently on GPUs, making these complex models actually competitive to train.
So we have this flexible framework, expressive memory, robust learning. How does this all translate into actual performance against the state of the art?
The results are, well, they're pretty overwhelming. On standard tasks like language modeling and common sense reasoning, all three Miras variants consistently outperform all the baselines.
And the baselines here are serious contenders. We're talking Transformer, ++Mat, RetNet, Mamba 2, and the Miras models do this with no attention at all.
That's the key. They are pure recurrent. It really proves that the combination of that deep MLP memory and these tailored objectives is just a fundamentally better way to manage long-term context.
Do you see that in the scaling patterns too, right, in Figure 3?
Absolutely. As you increase the context length all the way up to 32,000 tokens, the Miras variants just scale so much better. They maintain lower perplexity because those advanced retention gates like KL divergence stop the memory from degrading over those long distances.
And because they're efficient, they also win when you compare them on a fixed compute budget. More bang for your buck, essentially.
But the final test, the real stress test, was on recall-intensive tasks. Specifically, the needle in a haystack task.
Where you have to find one tiny fact buried in a sea of irrelevant text.
The ultimate test of long-term retrieval. And the results here were stark. All the Miras variants just crushed the baselines. Mamba 2, DeltaNet, you name it. Their ability to dynamically manage that MLP memory just pays off massively.
And you mentioned Moneta earlier. This is where its specific design choice really shone through, right?
It did. Moneta, with its generalized LPULB objective, had the best performance on a version of the task where they injected synthetic noise into the text. It confirms the whole thesis. You can design a model for a specific failure mode you want to avoid, like being distracted by noise.
So what does this all mean for you? I think the key takeaway is that the power of these new models comes from the synergy of two things: that really expressive two-layer MLP memory and the intentional, tailored choices for bias and retention. This is a design framework, not just one new model.
Absolutely. Miras gives you a blueprint.
Yeah.
It forces you to be explicit about how your network should prioritize information and how it should handle the past. It shifts the whole conversation from how big is the model to how smart is its memory management.
Right, and for me, the most memorable insight is breaking that monopoly of telltale 2 regression. Using something like Huber loss means you can optimize for things like robustness or stability, getting these tailored strengths that we've been missing in the transformer era.
And as we close out, we're left with a final provocative thought. The framework suggests that forgetting in AI is actually a retrieval challenge, not an erasure problem.
So if we connect that to the bigger picture, it raises a huge question. If these networks can be designed to learn how to manage and access a fixed-size memory in more and more flexible ways, what does that imply about the theoretical limits of artificial cognitive capacity when faced with, endless streams of data?
If the limit isn't capacity, but retrieval skill,
Mm-hmm.
well, the future of long-context AI is wide open, something to mull over until our next deep dive.
Indeed. Thanks for joining us for this deep dive into Miras. We'll see you next time.